Okay, so what you're looking at here is a graph. It definitely has an arrow going one direction, has an endpoint on the other. There's going to be a couple things I want to review from yesterday. We have a couple new vocab words here today. First step, let's talk about, let's do a quick review of how to evaluate a function. So evaluating is when they take your function, let's say this is f of x, which it is, that's the name of the function, and they say, I want to know what the value of 3 is. So what that means in notation, it's substitution. You're plugging 3 into the picture and you're going to tell me what the y answer is that's coming out of that thing. Because this is equal to the y number. So when I plug in 3 is on the x-axis right there, what was the y number? 0. That's your answer. Okay? That's substitution on graphs, right? You're finding what that number is and when it's evaluated to that. It could be any number. It could be f of -1. And I want to know what's the y number that your graph is hitting at -1 on the x-axis. So -1 is this, so where did the graph actually hit? 2. Boom. Make sense? Okay. That's how you evaluate a function. That's how you substitute numbers in. You can substitute anything in there, but I'm looking for, certain numbers. We had to do that in the last homework. I think those are like your page 159, 65 through whatever, okay? They still apply. They're not going away. We're still going to do that in these later sections. But the new stuff now, the stuff I introduced yesterday for the first time is like domain and range, but going more specific, like where is the domain of this thing where it's increasing? So increasing, let's go through the formal definition of this. So this is something we didn't talk about yesterday on the formal definition. The increasing for the domain is on an open interval. When I mean by open interval, you can go to the left and right side of it. On an open interval, any spots where f of x turns out to be greater than f of a. And what they mean by this is that A's points are anywhere like over here. So A would be over here somewhere, like on the x-axis, so like A is over here. And x is somewhere to the right of it. So over a towards x, anytime you plugged in an x, the numbers got bigger, right? When I plugged in numbers into my function, these numbers always tended to be bigger, larger than what f of a was, wherever a is at. So what that means is that it's actually going up. The numbers are actually increasing as the numbers get, as you go from left to right on this graph. That's what you're seeing here is the kind of the quasi definition of an increasing function, that it's always going up as you plug in the bigger numbers, because as you go to the right, those are larger numbers. That's increasing. But what I'm looking for over an increasing interval is that notation for domain. So what you do is you look at all these x numbers, and so I'm going any x numbers this way, going towards this way. Where's this thing going up, like to the right? Where did it start climbing as I went from left to right? So what was the smallest x number on this side over here? As I went to the left, what's the smallest x number that I have?
-5.
Past that, keep going.
Negative
Infinity, because the reason why we don't stop at -5, it has an arrow. So that keeps going forever. If it was a dot, it would have been right, but -5, we started there. But in our case, we're going from -infinity, and you can't include that number. And it looks like it's climbing. I know there's an arrow, and this really throws people off. It is actually climbing as I go left to right. It's going up. So from -infinity going up, it's still climbing. And I know it's going to dip and stuff, but it's still climbing. It's never actually going down. It's never turning directions. And at this point, as we keep climbing, when's the point where it turns? 1. So at 1, we're stopping there, because after that it starts decreasing. Notice I'm using strictly x numbers, not using y numbers. That's the interval where it's increasing over the domain. I'm not using a bracket here, because the number 1 is shared between the increasing and decreasing side. It actually turns directions. It's that inflection point where it actually turns. So it's not included in each, because it actually is the kind of the end cap. Questions on how you write the interval for increasing on this picture? Now, at any point on this graph, did this thing level off and go flat? So it doesn't have any constants. What a constant is on an open interval, so let's do that. It doesn't have any, but But if we're going to do a constant for a domain, like where it goes flat, on an open interval, we're looking for whatever a number you're plugging in, x number, somehow they turned out to be exactly equal to each other. No matter which a you picked and x you picked, it like leveled off. It'd be like if your graph was down here, and for some reason in this little band, it just kind of leveled off and then it kind of did its own thing, kind of like that. This area right here, it leveled. It didn't matter if this is a and this is x. When I plugged them in, the values were all the same. It like leveled for a while. That's a constant function. That's a constant domain for a little while. But we didn't have any of that because on our graph it kind of went up and then it just went back down. It never leveled off for a while. So now the next part is where it's decreasing. So where is my function decreasing over an open interval? So decreasing is anytime you're plugging in the later numbers, like the x numbers, x's are down here, a's are down here, you know, wherever they're at. There's just kind of some weird space in between there. But somehow these turn out, the x's turn out to be less in value than the a numbers were. So that means it's going down in value. So where did it start dipping? What was the first x number where it started going down? 1. Started dipping there. So open interval at 1, because we can't share that number, share between increasing and decreasing. And then when did it stop decreasing? 3. And since there's no arrow and there's nothing connected to it, you can actually put a bracket there. It stopped. There's an endpoint. So it's really not an open interval on this right side. You know, it actually terminates at some point. So it's actually closed. That's why we have the little, we have the actual box here, actual bracket. Questions on how notation works for domain and range, or domain I should say, not range. Okay, that was something new we talked about yesterday. I didn't do the formal definitions of it. I just went in the intro yesterday what we're going into. That's a big deal. The most common mistakes people make on this next test is this stuff. They forget when to put a parenthesis, when to put a bracket. They just don't understand how to do it when there's multiple parts where it's going up and down. So we're going to look at that in the next couple of pictures. Okay, now, one of the other things I want to discuss is that idea of an absolute or relative maximum and minimum, that type of thing. On this particular problem, this thing does have a maximum. There's like a height where this thing won't go past. It doesn't have a minimum because the arrow, and this is an ending point, so we typically don't list the end caps where it closes off. So this thing does have a maximum. Let's talk about this type. So there's two types of maximums. There's absolute, which nothing can be higher, and then there's relative. And we're going to look at some other pictures where we can see the difference between relative and max and absolute. But on this one, is there a highest point to this graph? Yeah, what's the number on that highest point? 4. You're always giving me that height number, which is 4. Preferably, I would like that if you're going to list an absolute max, you actually just give me the coordinate for it. That's what I prefer, but I can understand if you're going to tell me the maximum is 4, I understand what you're saying there. That's the height that we reached. Okay, questions on what the absolute maximum means. Nothing can be higher than that point. At some point, if there's another one down the road, then this coordinate would not be the maximum. It wouldn't be the absolute if there's something higher than that. Now, yesterday I didn't give you the formal definitions of it. The idea is that for every x that's on an interval from like a to b, so for some x that you're plugging into your function over an interval from a to b, and that could be an open interval, you know, that type of thing where there's arrows and stuff. This f of x somehow turned out to be greater than f of a, and f of x turns out to be greater than f of b over that interval. So it was greater than both values. And a would be like right here, this would be like a, this would be b, and x is that number right here in the middle. So when you plug those a's and b's into your function, somehow they turn out to be both less than the x number, the number in the middle of it. That means it's like a hilltop. The numbers around it are smaller, so it's a hill. It's a maximum value. That's an interval, and we're going to be greater than that. So this is like the notation that the book uses over the interval from A to B, that x happens to be a peak. It's bigger than both numbers on the end caps. Questions on what a maximum means, that the things around it are smaller. It has to be a hilltop, by the way, for it to be considered like a relative or an absolute. Now, if it has an end cap, I can understand that, but we don't consider end caps like this to be relative mins. It could be an absolute maximum or an absolute minimum, but we don't consider it a relative. Relatives have to be a hilltop, like I'm explaining here. Okay, on this one, we don't consider that to be a minimum because this thing keeps going forever and ever and ever, so it's not considered a relative. Relatives have to have like valleys. Numbers right have to be either higher or lower than that. Let's see, can I use this? Doesn't look like I can. Okay, let's go to the next one. Okay, perfect. All right, so this picture is going to explain when you have multiple situations going on here. We have an open interval, it's increasing for a while, it's decreasing for a little while, it's increasing again, then it's decreasing. So we have a couple different sets here. So if I want to do the interval where it's increasing, so we'll talk about that. So the interval where this thing is increasing. The leftmost point, is it going up right here? Yeah, so it's climbing and it's going up to what, -2? So from negative infinity, because there was an arrow, up to -2, that thing is increasing. Then it stops for a while. Notice I didn't include it because it's shared. It went down for a while, then at 0, so union, at 0, it starts climbing again up until about 3, where it turns directions again. When it switches from like positive slope to negative slope, that's where it switches, so that's why I stopped at 3. This is the interval, the domain, where this thing is increasing. Does that make sense, like how you do unions of these things together? Like, because I'm picking these bands from this direction all the way up to about 2, and then from 0 up to 3, that's where it's increasing. It's going up to the right. Everything else should be decreasing. So then decreasing's set. Can somebody give me the notation, like how am I going to write this decreasing part? Where's the band? What's the domain? Say it again. Somebody just start to say it.
-2 and 0 with parentheses.
-2 and 0 with parentheses, and union?
3 and negative infinity.
3 and positive infinity.
Oh,
Because you're using the x's, positive goes out. Yeah, positive infinity. Okay, there's your increasing, decreasing. Does this thing ever level off? So there's no constant. Okay, does that make sense, like how you can do it if there's multiple breaks in the graph? If there's end caps, let's say there wasn't arrows, there was end caps, you could just put brackets on the outside, because maybe those are end caps. We'll see a couple of those pictures later. Okay, does this thing have an absolute maximum? Yeah, what's the spot? -2, 4, okay. Does it have an absolute minimum? No. This thing goes forever down. It points towards negative infinity on that y-axis. So there's no minimum, absolute minimum. But it does have a relative minimum. There's like a little valley where the numbers around it are higher than than that valley. What is 0, 1? That's considered, now this is the first time you get to see this, this is considered a relative minimum. It's not the absolute minimum, but it is a valley. By definition, the points around it are higher than the point in the middle. So it's considered a relative min. Because you can have multiple relative mins in a problem that could be different numbers. It's just where you have little like valleys. Maximums, we do have the absolute, right? That was -2, 4, but there is a relative maximum, like another little hilltop, where that was what, 3, 2. That's a relative maximum. It's not the absolute tallest point, but this is a relative spot where it does hit a peak. So that's a relative max, not the absolute tallest point. Makes sense how relative works versus absolute. You can have a lot of relatives, but only one absolute. Okay. They're going to still ask questions on these types of things, like what's your y-intercept? What's your x-intercept on this one? My y-intercept is 1, my x-intercepts are -4 and 4. Does it pass through the origin? No, it doesn't hit 0, 0. That type of thing. So they're going to still ask like a series of questions that you guys are always used to that we've done in the previous sections. So just kind of be aware of that. That this problem they're going to have like they're going to give you a graph and they're going to ask you a series of questions about it. So this homework is pretty straightforward. You'll have like this graph and 10 questions after it about what numbers you're hitting and what the intervals are and stuff. So that'll come later this week. All right, same thing here. Now on this one, now we have constants. It leveled off for a while. It has increasing parts. The reason I brought this up is that weird bend in the road always throws people off. They don't know how to write the bend in the road when it's increasing. Let's do constant here. This thing doesn't go down at any point, but we can throw in a constant now. Okay. Can somebody give me the interval where it is increasing? Say again?
I don't think I will.
No, say it again.
-2,
-2, up to?
2,
Higher than that.
4.
4. That you're increasing. Even though there's like a bend in the road, like where it changed slope, it got like a little more steep. Do you agree that it was still increasing over that band?
Yep.
You know, it just got faster. How it increased. It's still increasing. So that's the intervals from -2 all the way up to 4. You didn't have to include the band, like where it switched all of a sudden, like where it had a little flex in the road, because it's still increasing the entire time. That's all they care about. They don't care that it changed slope. So it's increasing from -2 up to 4 on the x-axis. Now, for constants, where it leveled, it was constant from -infinity up to -2 on the x-axis. So it was constant. And then we do a union where it started again at 4 and goes to positive infinity. And again, I'm only using x numbers. Just use x numbers, not the y numbers. That really throws people off. Questions on how I did that? Like how I did the constants where it leveled off. Notice that when I write my parentheses, it's always the smaller number on the left, bigger number on the right, anytime you write them. So just be careful of that. Some people start flipping these around and they start counting wrong. Okay, so does this have an absolute maximum?
No.
It does have a peak though, which is weird. It's not like a hilltop, it's not like a relative, but there is a maximum height, which is 2. Now, I don't know the coordinate, there's a lot of coordinates that give you an absolute, but is there any point that's higher than 2? No, that is, so if you're ever asked like, does this have an absolute maximum? It does, even though it's not like a hilltop. It does have a highest point. It does have a lowest point, which is -2. Now, those are not considered relatives, because they're not like little valleys and stuff, but it is a highest and lowest point. So it does have absolutes, it does have both. It doesn't have any relative stuff. This is my last picture I'm going to show you here, then we're going to get to the other stuff. This one has, it has the end point, so this is a closed interval, there's no arrows on it. It does have a lot of increasing areas. You know, it increases from -5 up to 4, -2 up to 0, 2 to 4, it increases a lot, like there's like lots of bands where it's going up. Have a lot of decreasing spots, there's 3 bands where it decreases, and there's going to be end caps on the outsides, because there's no arrows. So you'd have brackets on the very outsides of those bands, except for certain ones. It does have a lot of absolute maximums. It actually repeated the absolute maximum 3 times and the absolute minimum twice. So just kind of keep that in mind. So if it asks for an absolute max, I would just say 4. But if you're going to give me coordinates, you have to give me all 3. So, okay, questions at all about absolute or relatives, like the differences here? Okay, let's get to the new stuff today. This is one of the last things we have to cover today. We have to talk about, it's called a differential quotient. I don't know if you've ever seen this before. I'm betting not. So let me stop the camera here. Okay, so let's talk about the differential quotient. Okay, this is what I'd like you to write down. I'd like you to write down this. It's something that should be brand new. It's the stuff that I was hinting at yesterday that this can be difficult for some people. Okay, Okay, so this is the function that we're going to be using. So 3x plus 4, that's my formula that I'm using. And what we're going to try to find is called a differential quotient. And this is the start of like some serious Calc 1 material. It's like the first kind of sections in Calc where we start and we kind of review like this from pre-calc. Because this is a major part of like doing the limits and whatnot. Okay, what a differential quotient looks like, it looks like this. This is like the generic formula that we use for differential quotients. It's like this go-to thing we use. I'll let you write this down, then I'm going to try to do my best to explain what we're doing. So a differential quotient, that is f of x plus h, and then we're going to subtract f of x, and we're going to divide it all by h. Okay, what you're actually looking at, like what this is trying to tell you, like what this whole mess of a thing is, it's basically a fancy way of saying we're going to find slope. And not just slope, it's actually an average slope. That's a word that you need to get used to. Average slope is something you guys did in Algebra 1 a lot. We did it in geometry a little bit when we did linear equations. But average slope is when you do this formula. Depending on once I write this down, you'll pretty much recognize this. And again, I don't care where the ones are and twos, but does everyone remember how you take y minus y, x minus x for slope back in linear equation days? Like that's, it's how you find slope on a line. You subtract the y numbers, subtract the x's, and that's n. That's your slope on slope-intercept forms. On this, y equals mx plus b, where this is the n. That's what we're finding. We're finding slope. That's called an average rate of change. That's what it is. Believe it or not, that's what this thing is. It's actually the difference in two y values, because f of x and f of x plus h represent y's, because it's the name of the function, so that's a y number. And on the bottom, they're actually doing this. They're taking the two coordinates that you used for your x's, and they're subtracting them. Well, when I subtract these, I don't actually need the parenthesis. And what happens when I subtract the x's? Yeah, you get h. And that's the whole reason why this is the formula. So it's a big fancy way of looking at this and saying, oh, we're finding an average rate of change, an average slope. Okay? Do you agree that this is a slope-intercept, or a slope-intercept form of a line? This thing represents y equals 3x plus 4. That's what it actually stands for. What's the slope of that when you look at it? 3. That's your answer. When you do the differential quotient, it's going to give you 3. And you're thinking, okay, Ward, you just told me the answer. Why do we have to do it? Because we use differential quotients for curves. So when you're going along a curve on a road, you do a differential quotient to figure out what the slope is at any exact moment, what they call an instantaneous rate of change, but we're doing an average over the long haul. So at any point on the curve, I can find the slope at that exact moment. Because like if you go north out of Garner here, they have that road that kind of like S shapes out of town. At any point, the slope could be different numbers on these curves, depending where you're going. Slope is where you have like a line. That's what slope is. That represents a curve. This thing, this formula, this crazy thing can give you the slope on any type of formula. It can be super difficult to do it though, because you have to follow the rules of what this thing is trying to explain. Okay? Okay. Does everyone understand the concept behind what we're doing? The overall view, we're finding slope. Okay, so today you get the first introduction of how to actually do this, so it will give you the number 3 out. All right, here's what I like to do. Because we already know the answer, so we're going to try to prove that it's 4. That is 3 in this case. Okay, this is my formula. So what I like to do, write a big fraction bar, put h on the bottom. We're rewriting that part I have in green, but we're actually plugging in your formula, the 3x plus 4 into it. Okay, so now on the top, we're going to have some function in the front where it has an x plus h, I'll show you that here in a minute, and then we're going to subtract the original function, the f of x. What was my f of x? 3x plus 4. So in the back, we're going to subtract the 3x plus 4. That's my f of x. We're going to subtract that thing. Notice I put it in parentheses because we have to subtract the whole entire thing, whatever the formula is. So what I just wrote down right now is this part. That's what I just wrote down. In the front is the function with x plus h plugged in to all the spots. So you're substituting x plus h into the function. So my function was 3x plus 4, but I'm plugging in, wherever you see an x, I'm plugging this x plus h into it. So this is the function up above. I'm going to put a bracket here, because it's going to get a little messy. It's 3 times x plus 4, right? That's the function, 3x plus 4. But instead of just an x, I'm plugging this into the x locations. X plus h. That's what you're doing. So if you have multiple x's in your problem, every x goes out and is replaced with an x plus h in that first bracket. That's what can make this difficult, so you have to kind of figure out how to write it. I'm sorry, I have no idea why my computer's beeping. Okay, are we good? Okay, we have to distribute the numbers in the top, we have to distribute that negative sign to the back. So what do I get when I distribute this 3? 3x plus 3h plus 4. Notice the 4 doesn't get a 3. In the back, I'm going to distribute the negative sign, so that's negative 3x plus 4. And this is all over h. Now, here's what I'm going to tell you if you did this right. If you did all of your steps, you plugged in the x plus h correctly, you wrote it down correct, you distributed the negative sign correctly, anything that does not have an h should cancel out. That's how you know you did this right. So on the top, what are the things that do not have h's? 3x's and 4's. They should go away. And if you look at that, they do go away. So 3x's canceled out because there was a positive and a negative. The 4's canceled out because there was a positive and negative. All you're left with on the top is a 3h. And what happens when you divide by h? You get 3, and that's a slope that I told you earlier. And you're thinking, okay, Ward, that was stupid. Did all that work and it just canceled out to be 3? Yeah, because this was linear. You told me right away when you looked at that problem, you knew the slope was 3 because it was a linear equation. It was 3x plus 4, 3 is the m. We can do this formula for the nastiest curve polynomial you've ever seen in your life. And what it does is it gives you a generic formula that helps you find slope at any moment on that curve. That's why it's super important, that you can find curves on any spot. So like what a civil engineer would do is if they're making a road, they can tell you the speed you should be traveling on the road so you can travel safely without flying off the curve. That's why when you go out of Garner, they're like, oh, this curve is rated at 20 miles an hour. Because at 20 miles an hour, you have full control of the car, the vehicle at a certain weight. It's like a generic weight of a car and a generic size of a car. If you go past that on a bigger car, you could potentially lose control of the vehicle and not be able to control on like an icy road or something like that. It's a generic number they came up with. Okay, I know that people, when they go north of Garner, they go way faster than 20. I understand.
Yeah, there's a guy who, like, must have been drunk or something, but you can see on the second curve, one of those arrows isn't a wood pole anymore. Is it? Like,
yeah.
One of them slammed into it and about flipped it in Altmaier's yard.
Yeah, so yeah, he's lucky if he didn't actually get injured in that. But yeah, there's a rating for that road. So in case the weather conditions don't permit, you can still have full control of the car and come to a safe stop. That's why they rate it at 20. If it's icy, 20 miles an hour, you should be able to stop the vehicle in a safe manner. Okay, that's the idea. Okay, all right, this is what we're going through tomorrow. It is difficult when you first start, like especially the problems I'm going to throw at you tomorrow. So be ready to go.